Today, we're going to talk about one of the absolute biggest challenges in AI. How do you keep making these models bigger and more powerful without them, well, just completely falling apart during training? It's a massive race to scale, but these titans of AI are getting almost too big to handle.
So that's the central question, right? Everyone's in this race to build bigger and better AI, but there's a huge engineering problem. The bigger you build them, the more layers you stack, the more unstable they get. It's like trying to build a skyscraper where the steel actually gets weaker the higher you go. Sooner or later, it's all going to come crashing down.
All right, so to really get the new solution, we first have to understand the old one. We've got to look at a concept that's been the foundation of AI for years and see exactly why it's now become a massive bottleneck.
See, for the better part of a decade, pretty much every deep neural network has used this clever trick called a residual connection. You can think of it like an information shortcut. It lets the signal from an earlier part of the model just skip ahead a few layers. This was a game changer because it stopped the signal from fading away. This one simple idea became the absolute bedrock of modern AI.
But here's the problem. What worked great for a while has now turned into a massive traffic jam. As these models get incredibly deep, you're forcing all of this complex information down one single path, and it creates a serious bottleneck. Just imagine trying to merge all the traffic from a major city onto one single-lane highway. It's just not going to work. It doesn't scale.
So what's the logical next step? If one lane isn't enough, you build a superhighway, right? Well, that led to a really intuitive idea that seemed perfect, but it turned out to be, let's just say, dangerously explosive.
And that idea was called hyperconnections, or HC for short. Instead of just one information path, you create a whole bunch of parallel streams. It's a multi-lane superhighway for all that data to flow through. And the best part was, it was designed to do this without adding a ton of extra computational cost. On paper, it looked like the perfect upgrade, a total no-brainer. But you knew there was a but coming, right? In practice, this amazing-sounding superhighway had a critical hidden flaw, a kind of structural instability that only really showed its ugly head when you tried to scale these models up to massive sizes.
And we are not talking about a little flaw here. This was catastrophic. When researchers tested this on a huge 27 billion parameter model, they found that these connections could amplify signals passing through the network by more than 3,000 times.
So what happens with that kind of amplification? Well, the signals literally explode. The whole training process just becomes wildly unstable, and the model's learning completely flies off the rails. You end up in this crazy situation where you're not even training the model anymore, you're just fighting its own architecture.
Okay, so how do you fix an exploding superhighway? Well, you don't tear it down. You install some guardrails. And that brings us to the hero of our story, a really elegant mathematical fix called the Manifold Constraint.
The full name is Manifold-Constrained Hyperconnections, or mHC. And the core idea is pretty brilliant. You force the way all that information gets mixed together to follow a very specific mathematical rule. It's like installing these perfectly designed mathematical guardrails that keep the entire flow of information balanced and under control. Now, the concept that makes this whole thing work is called a doubly stochastic matrix. I know, it sounds super complex, but the idea is actually incredibly simple. Just picture a grid of numbers. All this rule says is that every single row has to add up to exactly 1. And at the same time, every single column has to add up to exactly 1. That's it. That simple rule is the guardrail. It mathematically guarantees that information can get shuffled around and mixed, but it can never, ever be amplified. And if you have no amplification, you have no explosion. Problem solved. And here's where the story takes a really fascinating turn. The tool they use to enforce this rule, to build these guardrails, it isn't some brand new AI discovery. No, it's the incredible comeback of an algorithm from all the way back in 1967. It's called the Sinkhorn-Knopp Algorithm, and it is just beautiful in its simplicity. You start with any old grid of numbers, then you do two things over and over. First, you rescale all the rows so they sum to 1. Then you rescale all the columns so they sum to 1. You just repeat that loop maybe 20 times, and voila, you get a nearly perfect doubly stochastic matrix. It's that simple. I mean, just let that sink in for a second. An algorithm created over half a century ago for a totally different field of math is now the key to building stable, next-generation AI models.
It's just a perfect example of how sometimes this fundamental, old-school math is exactly what you need to unlock the future. Okay, so the theory is awesome, right? A stable information superhighway built with a vintage algorithm. But does it actually work in the real world? Let's look at the results. Because this new architecture isn't just stable, it's also fast and shockingly strong. And the difference is, well, just look at it. It's stunning. On the left, that's the connection matrix from the old, unstable model. It's a chaotic mess. Values are all over the place. And on the right, that's the new constrained matrix. It's perfectly balanced, stable, and orderly. The contrast is really night and day.
And that stability has a huge impact on training. With the old model, you can see these wild spikes where the training just goes haywire. But with the new constraints, the model's learning curve is just smooth and consistent. It's not just avoiding explosions, it's actually learning way more effectively.
And here is the real kicker. This isn't just about making things stable. It's about making them better. I mean, look at these numbers. Across a whole bunch of really tough reasoning and language tests, the new models don't just avoid breaking, they significantly outperform the standard models. They're not just more stable, they're smarter. Now, you'd probably think that all this extra math, these guardrails, would slow things down a lot, right? Well, get this. Because of some really clever system optimizations, this whole sophisticated architecture adds only a 6.7% overhead in training time. That's tiny. And that's what turns a cool theory into a real production-ready blueprint. So let's step back and put this all together. What does this innovation really mean for the future of AI? What's the big picture here?
I think there are three huge takeaways. First, topology matters. How you connect the layers of a network is just as important as what you put inside them. Second, constraints can actually unlock power. Sometimes adding smart rules to the system is what enables you to build entirely new and more scalable things. And finally, this just proves that the future of AI is this deep collaboration between abstract math, hardcore systems engineering, and AI theory. You need all three.
And I think this quote from the researchers just says it all. They write, "It is not an incremental tweak. It is a blueprint for how large language models may scale next." This isn't just about making today's models a little bit better. This is a whole new roadmap for building the true titans of tomorrow.